but is not actually necessary to understand the random walks on these graphs themselves, which have other interesting behavior and questions associated to them. But I will explain some of the motivation. I'm not going to go into deep detail. And I'm not quite sure the background of everyone. I know that some people will know more than others about certain topics, so you can feel free to ask more details than I give. So let me start by just saying what I mean by dyadic lattice graphs. And this is something that probably you have seen in various contexts or some version of this. So it's an infinite graph. And the idea is that it's made of these squares. And on the bottom, you subdivide into two pieces, and then you put two squares below that. And you keep going forever. Okay, the squares get smaller and smaller. Now, but you can also go upwards. Now notice if I'm at a given level, there are two ways of extending upwards, right? The way I did, or I could have an edge here and an edge here, right? So every time you go up, there are actually two different ways of doing that. But from any level, any horizontal level downwards, there's only one way of doing it. And it doesn't matter where you are in the graph. From any level down, it looks the same, okay? Now, this is a planar graph, and the motivating question is actually about relationship of random walk on the graph to random walk on the dual graph. So here is the planar dual. I put a vertex in each face, and I connect to such vertices by an edge when the corresponding faces share an edge. And so this is also a graph that you may have seen before. It's like a binary tree going down each time, except that it has horizontal edges connecting all the levels, all the vertices at a given level, okay? Now, these graphs can actually all be seen inside the standard Cayley graph of the bounce-like solitary group, which has this relationship here, presentation here. In the following way, the up and down is switched. But remember when I said that when you go, sorry, up and down is not switched. When you go up in the dyadic lattice graph, there will be two choices. And that corresponds to these two branches of the Cayley graph. So it's a little bit hard to see. The red edges are A edges and the blue edges are B edges. But so you can see for every edge from here to here, between blue, there is two going down. And then, but there are two ways to go up depending on which of the pairings you take. And so we can think of any choice of a dyadic lattice graph, which means a choice, infinitely many choices going up, as a choice of going up through the bounce-like solitary group Cayley graph. Now, this is just of curiosity as far as I know. It's not going to come in, not going to enter in any way into my talk. Let me talk more about planar duals. So here's a classical example, the hexagonal lattice and the triangular lattice. Here is in the hyperbolic disk. We have a Cayley graph, which is in black, and the dual, which is in light blue. And this is somewhat more relevant to my talk, because my graphs naturally lie in the hyperbolic plane. Now, so I want to talk about simple random walk. And first, let me just mention what happens on a finite graph. So simple random walk means from any vertex, you choose any one of its neighbors with equal probability and repeat independently forever. Being a finite graph, this graph will have a stationary measure for the simple random walk, which tells us the long-run probabilities of being at various vertices. And it's well known and easy to prove that the stationary measure is proportional to the degrees. So in this case, the degrees are 1, 3, 3, and 2. And so you weight the uniform measure by the degrees and renormalize to be a probability measure. And that gives you the stationary measure for the long-run probabilities for the simple random walk. So I can't see very many faces, so hopefully if you're not following, you Well, if you're not following, you should ask me a question. You should feel free to ask me a question. Now, I'm interested in infinite graphs. So here's a simple infinite graph. You can imagine how this goes forever. And there are two types of vertices, black and blue. And in fact, in this graph, there's a nice automorphism that will take any black vertex to any black vertex, or any blue vertex to any blue vertex. So there are really only two types of vertices, which are denoted by their color. Now, how many of them are black and how many of them are blue? What proportion is black and what proportion is blue? So this is where I want some audience participation. Two fractions that add to one for black and one for blue. What are they?
1/2, 1/2.
One half,
wait,
one half.
Yeah.
Why is that? Someone's saying they're infinite.
It's not 1/2, 1/2, is it?
Yeah, 2/6 and 4/6.
Well,
Say it again.
1/3 and 2/3.
When they're doing, why is that?
Because there's blue dots and for every 2 black dots.
Yeah, it's 2-to-1 map.
3 7s and 4 7s.
Okay, that's surprising. All these answers are wrong. I'm only
every blue dot has one black neighbor.
every what?
Every blue dot has
Right.
one black neighbor, and every black dot has 4 blue neighbors.
Right, so it's 1/5 and 4/5.
Correct. And so one way to say that is you could say for every black dot, if I go down and to the right, I see 4 blue dots. That's a 4-to-1 map. Simple local 4-to-1 map. Now, in this case, because this is all in the Euclidean plane, equivalently, you could just take a big box and count how many black and how many blue are in there and take the proportion. And what the argument I gave should convince you that it will be 4-to-1. Okay. Now again, if I do simple random walk on this, there won't be a probability measure on the entire graph that will be stationary. But I can pay attention to how often it's in a black vertex compared to how often it's at a blue vertex. Okay. Now, what will the answer be? I will take this, which is basically the uniform measure in some sense on the whole graph, and weight by the degrees. What are the degrees? The degree of a black vertex is 8, and the degree of a blue vertex is 3. So I weight by factors of 8 and 3. 8 times 1 is 8, and 3 times 4 is 12. If I renormalize, it's 8 over 20 and 12 over 20. So that's how long, those are, if you want, that's the stationary measure for black versus blue. Okay? Any questions on that? All right, here's a more difficult example. This is also quasi-transitive, meaning there are two types of vertices, black and red in this case. And again, so it's this infinite 3. Black vertices have degree 4, red vertices have degree 3. But this is not so adapted to trying to take a big piece and say, well, how many are red and how many are blue, and take a limit. But I claim there's still a good way to make sense of the proportion of vertices that are red and compared to the proportion that are black. How would we figure that out? Anyone have a suggestion? Yuval, you're not allowed to say. Well, the idea is to use in reverse this idea that we had for this quasi-transitive graph with two classes, okay? Here we said, well, we know what the proportions are of vertices, and that corresponds to like the uniform measure on a phonic graph, and we weight by the degrees. But we don't know the first thing here, but the second thing I claim we do know. How often is a random walk at a black vertex compared to a red vertex?
Right, so it'll be in a black vertex 4/7 of the time, and a red vertex 3/7 of the time. No,
That's not right either.
no, no. I guess it's not true because the other
It's
one
alternate.
didn't quite work that way. You first have to figure out the uniform measure and then wait.
It's 50-50.
By-
Every time every black vertex goes to
Yeah,
a red
yeah, yeah.
vertex and
Of
vice versa.
course. Yeah.
That's right. So the random walk spends equal time at black and red vertices. And so if you unbias by the degree, 3/7 of the vertices are black and 4/7 are red. In other words, if you multiply this number by 4 and this number by 3, you'll get equal numbers. Okay? Now, I'm not proving anything here. I'm just trying to give you some intuition behind the concept which is going to come up. All right. Now, we're interested in more complicated graphs. Here's one in the Euclidean plane. Comes from a certain nice tiling. But it's rich, which would be, it's naturally random. So this is what I want to talk about more. If we want to talk about a random infinite graph, then we should really choose a root, because the space of all infinite graphs is not a nice topological Borel space. Whereas if I fix a root, I can say how close two rooted graphs are. They're close if in a large ball around the root, they agree. But you can define a metric, and then you can define probability measures on rooted graphs. Okay, so that's important, first important thing of having a root. Second thing, it leads to this idea of unimodularity, which is what I was giving you an intuition for before. I'm not going to define it. It's part of the motivation, as I mentioned, but it really won't be needed at all to understand the talk. But unimodularity is a way, you can think of it as a way of talking about a uniform measure on the whole graph. And that, remember, this is going to be a random rooted graph. And the idea is that intuitively, the root is uniformly chosen. Now, that doesn't make sense because there are infinitely many choices, uncountably infinitely many choices in a given graph. But you can think about it that way. And that works very well for almost everything. And so when we think about random walk, if this corresponds to a uniform measure, then when we bias by the degree, this should give us a stationary measure for the simple random walk. And it does. Oh, I haven't told you the definition, but this is a true fact. And that's what I was giving you the intuition about. Now, this whole talk is really about planar graphs. And with planar graphs, obviously, it's important to talk about the dual graph. So it turns out that if I have a random rooted graph, which is planar, and is unimodular, then there is a simple way to choose the root of the dual graph. In fact, it will be in a face that has this root on its boundary. That will make the dual graph unimodular as well. And that means that the theory of unimodular random rooted graphs, which is a fairly extensive theory by now, can use results about dual graphs in a nice way. Let me just give you an example. So I was showing you some examples at the beginning of quasi-transitive graphs with two classes of vertices. Here I'm going to give you an example of a transitive graph. There's only one class of vertices, which is not unimodular. We take in black the three regular tree, and then we fix some direction to infinity. That's indicated by this arrow going down. Having fixed this direction to infinity, every vertex has two black children and one black parent. and a parent of a parent I will call a grandparent. So what I do is for every pair of vertices where one is a grandparent of the other, I add a new edge, which are colored in fuchsia here, okay? So for every vertex, there will be 4 new edges going up and 1 going down. So the degree will increase by 5. It'll be a degree 8 vertex graph now. Well, it's not obvious, but it doesn't take too long to convince yourself that this new graph is actually transitive. You can, for any pair of vertices, there will actually be an automorphism of the graph that takes one to the other. However, this new graph is not unimodular. And I'm not going to say why, because I haven't defined unimodular, but it's not too hard to prove. But just to give you an example, something bad. However, this will also, though, sort of indicate something about non-unimodularity, which is going to come up in these dyadic lattice graphs. Any questions?
I mean, quick way of saying it is that the automorphism group of the of this graph is some locally compact group, but it's non-unimodular.
Correct. That's equivalent for a fixed graph. Okay, so Nicolas Curien asked the following question. He was considering what turns out to be a somewhat more general class of random rooted graphs. Remember, the unimodular ones have this property that if I bias the probability measure by the degree of the root, it becomes stationary for simple random walk. But those are not the only random rooted graphs which are stationary for a simple random walk. So the ones that are, we call stationary random graphs. More precisely, what we mean by stationary is when the random walk takes a step, the root moves with it. So that's the new rooted graph. So he asked, suppose you have a plain stationary random graph. Is there, like there is for you in the unimodular case, is there a stationary plane dual? Is there a way to root the dual graph that will make it stationary also for a simple random walk? So the idea is how much of the theory of unimodular random rooted graphs extends to this more general setting. To make this question precise, and there's different ways of making it precise that are equivalent, we'll say the following. So suppose I have a probability measure mu on the space of rooted plane graphs. So G is the graph and O is the root. Now, G is not necessarily a fixed graph, right? G, O as a pair itself can be completely random. There can be uncountably many. Now we assume this locally finite, every degree is finite, and the same for the dual, which means every face has only finitely many edges. So let nu be the measure where you just choose a uniform face of O. Suppose mu is stationary, then is nu mutually absolutely continuous to a stationary measure? In other words, could you just change the weights to make it stationary? Like we could in the unimodular context. So we show that the answer is no. In fact, this dual measure nu might be singular to every stationary measure. And so if it is singular, that's bad news. If you want to use the theory of stationary random graphs together with duality, because then you're in a completely different space. So that was the motivation. But now I'm going to talk, and we proved it was no by giving an example, which were these dyadic lattice graphs. So from now on, basically, I'm going to forget the motivation and talk about this very specific situation. Now, there are uncountably many such graphs, even though going below every level, there's only one. Above, remember, there are countably many binary choices to make. That gives you uncountably many graphs. In fact, they're almost all different. We need a...
It's uncountably many rooted graphs.
Even unrooted.
even unrooted.
Yeah.
Okay.
The root, there's only kind of many choices of a root.
Yeah, I guess that's true because then you have a tail, right? Okay, sure. Yeah. I see. You have a tail sequence.
Yeah,
Right. If
right.
two
And I'm talking
tails are-
even up to automorphism, up to
Yeah.
isomorphism, I mean. So I need a good way to talk about the space of these graphs. So I want to give a coding. So the first thing is, for every vertex, I'm going to associate a bit, 0 or 1. Very simple. If the degree is 4, it's 0. If the degree is 3, it's 1. Okay. But what do? I want to now pick a root, like this vertex over here, and I want to say which dyadic lattice graph is this rooted graph. So this is what we do. It's going to be a left infinite sequence. It's, in other words, a dyadic integer. And the root is the most significant bit, which is at the right. So this is a 1, then there's 0, then there's 1, or really coming back the other way, it ends 1, 0, 1. How do we determine this? If I can go up, you just go up and report the next bit, which means at a 0, you can go up. But if it's at a 1, you can't go up. So then you move to the left, which is necessarily 0, and then you can go up, and then you report the 1. So from a 1, you always have to go left before you go up, but there could be either a 1 or a 0 up there. So you just report the first bit every time you go, the bit that you get every time you go up a level. All right?
Fibonacci.
Excuse me?
So some Fibonacci. No
Fibonacci?
You're not allowing two adjacent ones, but so the number of collection of sequences is a Fibonacci number.
Oh, this could have been a 1 here.
Yeah, but you can't have two adjacent ones
What do you mean by adjacent?
in your expansion. A 1 is
Sure.
always followed by a 0, right?
No. You always move through a 0 at the same level from
Yeah.
a 1.
I
But
know.
once you go up, you may end at a 1.
That's right. But if I just look at the sequence you wrote down, it has no two adjacent ones, right?
I only wrote down 3 of the bits.
Yeah, but if you write the infinite sequence, there are no.
Up here, there might be a 1.
Yeah, but it's not adjacent to another one.
Adjacent, it's adjacent in the sequence. It's not adjacent in the graph.
If you write down all the bits you see, including those when you go left,
Oh, if you write down all these zeros next to 1, sure, yeah.
then you would get the Fibonacci thing. Okay.
I'm not sure what you mean by Fibonacci sequence, but
I
okay.
mean, the golden shift, you can't have two adjacent ones, but
Oh, that's what you mean, yeah, I see, okay. Yeah, good. Okay, so is there any confusion left over about how we are notating our rooted graphs? All right, now here is a picture of the same kind of graph in the disk instead of the upper half plane. Here's our root. That going down is what's in black. There's only one choice. Going up, there's 2 choices every time, and that's in red. So for example, in this case, what is the rooted graph? It's ending 1, 1, 0, 1, 1, 1. How do we see that? We go in reverse. Here, this is a 1. So we go left and then up. This is a 1, left and then up. That's a 1, left and up. That's a 0. We go up 1 and so forth. Okay, that's how we saw that particular sequence. So this is what I'm calling gamma sub A for this dyadic integer A. And now I mentioned similarity to that non-unimodular example, which had this fixed end. This is analogous in a precise way to having this fixed boundary point in the hyperbolic disk. All right. Now, since we're talking about the dual graphs as well, we need to code them. And in fact, we would like them to be in the same space so we can talk about absolute continuity and mutual singularity. So it's actually very simple. They also have 0s and 1s. And what we do is we simply take the bit which was on the primal graph. So in the dual graph, this corresponds to face. We go in the upper left corner. We take that bit and just put it down there on the face vertex. Okay. And now we can always go up. So notice, for example, that going from here to here corresponds to going from here to here, which would go through this vertex of label 0, but now it's just 1 to 1 directly. So you just read by going up the tree. It's simpler. Okay? Never use the horizontal edges in the dual. Now let's talk about how this coding relates to simple random walk. So this is the same example I showed before. And remember, so we think of this as dyadic integer ending 1, 0, 1. Suppose we step 1 to the right. Then we're at the graph that ends 1, 0, 0, right? Instead of this blue portion, it would be this green portion. That would be the end, come to the root. Remember, so when we take a step, we move the root with us. So that's moving to the right in this example. If we move to the left, then that 1 would change to a 0. That's all. If we move to the left again, that makes a bigger change. Instead of ending 1, 0, 1, it's going to end 0, 1, 1. Now from here, you can't move up. If we were here, so that was moving right or left. If we were here and moved up, we would just take off that last 0. If we move down, well, when you move down, it's always going to be to a 0. It has to be a degree 4 to move down. So to move down is always going to just take the same sequence and append a 0 at the end, the most significant bit. Okay? This should remind you of arithmetic. When we move to the right, we add 1 in base 2. Move to the left, we subtract 1 in base 2. If we move up, which we can only do for an even integer, we divide by 2. If we move down, we multiply by 2. Any questions about that? Okay, so now I'm going to show you a simulation. And so I need to share a different window. Okay, you see this? It's actually covering up where I was just seeing you. Let me move you over here. Okay, so I'll just, so here, this represents the end, right? There are infinitely many bits to the left. Can't show them all. So we're at some graph which we're coding by the dyadic integer, and this is how it ends. So now let's take one. Yes, question?
So we're talking about like a random walk on the group of 2-adic integers where we're adding 1 or subtracting 1 or multiplying by 2 or dividing by 2 if we can.
Right.
That's the okay.
Correct.
Wanted to I just wanted to rephrase it.
Yeah.
Okay.
Right. Okay. So I'm going to take one step here. I just went down, right? Let me go back. What's the difference? Added 0. That means going down, right?
Yeah.
Okay. Another step. What was that?
It must have been dividing by 2.
No.
No? That was that adding 1? I missed it.
Subtracting.
Subtracting 1. Oh, I see.
Subtracting 1. Right, which is moving left. Okay. Then we moved right again, right? Move left. Moved right. Down. Left. Right. 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 Up. Right? Okay. So I think now you can imagine how it goes, right? So let me just make this go faster. What do you notice?
It's growing fast.
It's growing, right? Okay, so here's 10,000 steps. Okay, why is it growing? All right, so let's go back to the talk. No, let's see here. Okay, so why was it growing? Oh, sorry. Let me first. Well, the other let's talk about why it was growing. Why was it growing? So maybe it's better to go back where you see more of this.
There's always a way down. There's only half the time is their way up.
That's right. So there's a drift downwards, which means growing. Okay, this is going to be a key factor. Okay, so let's look at random walk on the dual graph with respect to this coding. It's actually going to be identical, except for the fact that there's different possibilities for moving. So here we were ending at 1, 0, 1. If I move to the right, it ends at 1, 1, 0. Move to the left, 1, 0, 0. Move to the left again, 0, 1, 1. But now you can always move up, which means dividing by 2 and we're throwing away the remainder. In addition, there are always 2 ways to go down, appending a 0 or a 1. Okay? So it's multiplying by 2 and possibly adding 1. All right. So we remember we're interested in stationary measures. And if this dual graph is actually simpler to talk about. I claim there is a unique stationary probability measure for simple random walk, and it's just the Bernoulli 1/2 process. In other words, all the bits in this dyadic integer are independent, equally likely to be 0 or 1. So, why? Well, the drift downwards implies that no matter what graph you start at, no matter where you start, the distribution as a rooted graph, remember the root is going with you downwards, converges to the same measure. Why? Remember, below any point is always the same graph in every graph at every root. Since it's going down, whatever there was above that was unknown goes away to infinity. So there's only one possible limit. Now, why is the limit Bernoulli 1/2? When we move up, so remember, we're on left infinite, the dyadic integers are left infinite. When you move up in this dual graph, right, that's just getting rid of that rightmost digit. That's the right shift. And I got it there, right? It's a right shift on left infinite sequences. That definitely leaves invariant Bernoulli 1/2 measure. What if we move down? That's the left shift, and but you add a new most significant bit, which is equally likely to be 0 or 1. Also leaves invariant Bernoulli 1/2 measure. Now our horizontal move is either going to move to the right or to the left, equal probability. This is addition. This is the most complicated move, right? Addition mod 2 in dyadic integers. The dyadic integers is a compact group. This is also known as the odometer system. And adding plus or minus 1 with equal probability leaves invariant the harm measure. This is a group addition. So it also, which is Bernoulli 1/2. So it also leaves it invariant. A random walk is a mixture of these. 1/2 chance, you move up. 2/5 chance, you move down. There were 2 ways. 1/5 to move left, 1/5 to move right. All of them leave it invariant. So the whole mixture also leaves it invariant. Since there was unique invariant stationary measure, this is it. Okay? Yeah. Now what about the primal graph? That's more complicated. The theorem states much less. There's a unique stationary probability measure for simple random walk on the primal graphs. And the proof is much shorter, and it's the same. For the same reason, because the random walk moves down, it converges to a unique measure. Unfortunately, we don't know what the measure is. First of all, we can say it's not Bernoulli 1/2. So let me prove that. There are two, so I'm going to pay attention in particular to vertices of degree 3, which means a bit, the most significant bit is 1. And I want to claim the probability of that is not 1/2, okay? Now, if a vertex has degree 4, then the vertex above it could have degree either 3 or 4. Let P4, 3 and P4, 4 be the corresponding probabilities for our stationary measure. This is a decomposition, a partition of the space into 3 pieces, so the probabilities add to 1. Now let's look at the property that it is stationary. So that means if we take a single step, the probability that we're again at a vertex of degree 3 has to still be P3. So P3 equals, well, you could start at a vertex of degree 3. Now, what's the chance that after one step you're at a vertex of degree 3? 0, right? 1 is only surrounded by zeros. What if you're at a vertex of degree 4 whose upper neighbor is degree 3? What's the chance of ending at a vertex of degree 3? 3/4. 3 of the 4 neighbors are degree 3. What about 4, 4? 1/2. 2 of the 4 neighbors are degree 3. So we have this equation that relates these 3 probabilities. Now, 1/2 is less than 3/4. And this is 0. So this is at most P4, 3 times 3/4 plus P4, 4 times 3/4. And these two, by this equation, add to 1 minus P3. So P3 is less than or equal to 1 minus P3 times 3/4. So that means P3 is less than or equal to 3/7, which is less than 1/2. So that's why P3 is not equal to 1/2. Okay? So this says that the two stationary measures are not equal, but that doesn't say anything about whether they are mutually singular, which was our question, or our claim. It's our theorem, right? And in order to answer this, we actually need to look at harmonic measure in the following sense. So gamma plus is what is below any vertex. So it's this graph over here. Nothing above, just what's below. Okay? It's an infinite graph. That's gamma plus. This graph has a nice automorphism. If you just shift everything by 1 unit, it's the same graph. And so we will just we'll take the quotient by that, wrap it on a cylinder, and you get this graph, which I call gamma circ. So this point is going to be identified with this point, and there's 2 ways to get to it. So at the top, there is this left side and the right side are identified with each other. So these 2 vertices are the same, and these are 2 loops. But then over here, you have this goes back to itself, and so on. So that's this new graph, gamma circ. I want to label its vertices. At the top, I will begin with the empty string, and then I'll use the same bits I had before, 0 and 1, but just keep concatenating. There's no infinite past. I'm starting with the empty sequence. And so I can just keep going by adding the next bits to the right. So this is my coding of the vertices on this little graph, cylinder graph. What do I mean by harmonic measure? Well, I'm still doing simple random walk. It's obviously still going to go down, and there'll be some limiting right infinite string. The probability measure of that limiting right infinite string is called harmonic measure. Because of the self-similarities of this graph, it is invariant under the left shift. Right? If I take out the left shift, that chops off this top level with infinite strings. The 0 and 1 disappear, they become the empty string, and then what I see below is just the same kind of thing, but doubled over. So it's just the same kind of thing. So here the graph is. Let me show it to you. This will be useful in the Poincare disk. So here's the root, the empty sequence right over here, and there are these two loops. Then you go down, and you can go back to the middle or back where you started. Right? You can go down again, and then there's more places to stop. So you go back. Okay? Any questions on this picture? Okay. It's going to be useful to identify the right infinite strings of bits with the unit interval in the obvious way, base 2. Now this graph, gamma circ, is symmetric under reflection in the midline, right here, okay? So if I talk about the harmonic measure, the probability that you end up in this half, it is the same as the probability that you end in this half. Remember, this vertex and this vertex are the same, okay? Here, we're showing the similarity in the disk. So this midline here is this line over here. Now, reflection in this line is actually the same as reflection in these two lines, which are the same line, and that's over here. So the top and the bottom, as you can see in the picture, are symmetric. Now let's look a little more closely. So ending up 0, 0, that means you're ending up in this half. Ending up 1, 1 means you're ending up, sorry, 1, 0. Sorry, 0, 0 means it's ending up in this quarter, and 1, 1 means it's ending up in this quarter, whereas a 0, 1 or 1, 0 would be ending up in this quarter or this quarter. So 0, 0 or 1, 1 are in this quarter or this quarter. 0, 1 or 1, 0 are in this quarter or this quarter. Okay. First of all, I just grouped those into two pairs of bits, the red and the blue. So I claim that the probability of having 0, 0 as the first two bits in your harmonic measure is the same as 1, 1. And likewise, 0, 1 is the same as 1, 0. That's because of this symmetry in the midline, right? We're starting right here in the middle. So you're equally likely to end up above as below. Right?
Yeah.
But what about the left compared to the right? I claim that these have strictly greater probability than those. The ones on the right are strictly greater than the ones on the left. Why is that? Anyone have an intuition? No? Remember, we're starting right here.
Mhm.
We're starting in the right half. Actually, there's no analogous vertex of this one on the left half, but from here you have to go here, which is analogous to this one. So it doesn't really matter. You can start here. The point is, the left and the right are the same, but you're starting in the right. So it's more likely you're going to end up in the right. Now, obviously, this requires proof because we're going to need the fact that it is strictly greater. One can prove this, but it should be intuitive now. Okay. Any questions on this? All right. So why are we looking at harmonic measure? Here's the key fact. Let sigma be a finite string of bits. And let's think about the stationary measure under primal graphs. That means it's a probability measure on dyadic integers, left infinite strings. Okay. Claim is for almost every, with respect to the stationary measure, dyadic integer A. Let's look at the asymptotic frequency of this finite string sigma in A, meaning you see how often you have sigma appearing in A as you run off to infinity. Some limiting frequency. That's what we mean by the asymptotic frequency, okay? Like how often do we see 0, 0 next to each other? The answer is it's equal to the harmonic measure that we've just been talking about of the set of strings that begin with sigma, which is what we've been talking about. So the frequency of double zeros is equal to that harmonic measure of beginning with 0, 0. Now this is the least intuitive part of the talk. Let me try to give you some intuition. Well, actually, before I give you the intuition, let's say why this is useful. So, for example, the asymptotic frequency of 0, 0 is therefore strictly larger, almost surely, than the asymptotic frequency of 0, 1. Because the harmonic, we just saw that for the harmonic measure. In other words, the stationary measure has a certain almost sure property that Bernoulli 1/2 measure does not share, which was the stationary measure for the dual. And that's why these two measures are singular. Okay. Now, what's the intuition behind this key theorem here? So for the stationary measure, we're measuring this frequency of sigma as it goes along, as it recedes into the past, if you want. What about the harmonic measure? Well, sigma is what's left at the beginning as the random walk goes down to infinity. So there's a similar idea in that, compared to the random walk, the bits that we're looking at recede infinitely far into the past. But it's a similar random walk. One is stationary and one is, well, you've forgotten what's above some limit level, but that's not going to matter because that is only visited finally often. Okay, that's pretty vague, but that's the intuition. And it is a theorem. It was very painful to write the proof, actually, but it's true. Okay, so I see someone clap, probably someone who has to leave because it is 1:51 your time. So this is just reminding you of this demo showing how things recede into the past. And it would be valid as a demo even for the harmonic measure. Now, okay, so for those of you who still have time, that's the end of the proof of the main theorem, but there's a few things to say that are very puzzling about this harmonic measure, actually. Now, this harmonic measure, remember, this was on this graph, and I said that it was invariant under the left shift. And we just proved that it was not the big measure, and therefore it is a singular measure. And this is supposed to indicate what it looks like. Obviously, it's difficult to give a picture of a singular measure. So this is an approximation. We took intervals of length 2 to the minus 14. And for each of those intervals, we approximated what its harmonic measure was by going down to 2 to the minus 20, actually. And took that measure and multiplied it by 2 to the 14 as if it were a density. And so we have a dot. There are 2 to the 14 dots here, 2 to the 14 times the harmonic measure. And then notice the scale here. 0.9 down here is 1.3 up here. Pretty close to 1. But we know that as we would take finer and finer approximations, almost surely everything would go to either infinity or 0. So apparently it's going pretty slowly. Now, remember there was a symmetry of reflection in the midline. You can see that clearly here, right? And you can see reflections similarities in 1/4 and 3/4 and so on. But notice the way that I have put the tick marks on the bottom, they're multiples of 1/12. That's because there's something else interesting happening. Where are the biggest dots and where are the smallest dots? Does anyone see the pattern? 'Cause 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 'Cause
fractions with dyadic denominators give you highest.
Well, let's see. The biggest ones are 0 and
Third,
1.
but you have a third at the bottom.
Yeah, a third and 2/3, actually, right? Of course, they have to be the same by symmetry. So 1/3 and 2/3 are the minimum.
Mhm.
1/6, well, actually 5/12 and 7/12, I guess, are the next smallest, right? 1/6 and 5/6. Okay, yeah. So why 1/3 and 2/3? Those aren't very dyadic sounding.
But there it's lower, and at the dyadics it's higher.
Yeah, what does that? Yeah. So what does that mean? Is there something more precise that one can say? What's special about 1/3 and 2/3? The very lowest.
Lots of ones in the binary expansion.
That's true for any number getting really close to half. Well, what is 1/3 in base 2? It's 0.01010101, so forth, and 2/3 is 0.1010. What's special about that? Strictly alternating, right?
Uh-huh.
Okay, so actually, let me show you this graph. It's almost the same, but now it's just every interval of length 2 to the minus 12. The color indicates the number of bit changes, one to the next successive one. The dark ones have few bit changes, and the light ones have more. The dark ones are on the top, and the light ones are on the bottom.
Yeah.
Why is that? Well, so
you argued that 0, 1 has low harmonic measure, so and 1, 0. So somehow alternating is costly.
yeah, that is actually the right explanation. It goes back to this pink versus blue or red versus blue that I was showing you before. But let me give you some more precise things, which will still lead to a puzzle. So here's a harmonic measure without the colors. And the other thing to notice here is there's a weak dependence between the first bit, right? Is the first bit a 0 or 1, and the others. So this is not a question of reflection, the first bit compared to the others. So there's a standard way of looking at this. Let's call for a sequence of bits, xi. Let's call P of ix to be the harmonic measure that the first bit is I, given all the other bits.
Mm-hmm.
So given all the other bits, was it this half or this half? Okay. In particular, we can take x and replace I by x1. What's the chance that the first bit is x1 when you know the other bits of x? So these conditional probabilities only make sense for harmonic measure almost every x. We call that g of x. There's a nice relationship between g and harmonic measure. So let's consider the harmonic measure of the interval 1/4 to 3/8. These are the numbers in base 2 that begin 0, 1, 0. And after that, anything. We can use g to get a certain formula. Because of shift and variance, whatever follows this has the same measure as nu h. Call that y. So we take nu h of y. Then we say, well, there was a 0 before that. What was the chance that there was a 0 before that if everything else was y? By definition of g, it was g of 0.0y. Given that, what's the chance that there was a 1 before that? It was g of 0.10y. Given that, what's the chance that there was a 0 at the beginning? It's g of 0.010y. And so this measure is equal to the integral over the whole interval of this product of 3g's, where we shift each time, and then you have harmonic measure at the end. You could do this any number of times. Question is, could you do it infinitely many times? In other words, and forget nu h. Does this function g determine the measure nu h? That's called a g measure in ergodic theory. It's like 50 years old idea. Well, there's somewhat of a problem for that because I only define G almost everywhere with respect to harmonic measure. So let's see what G looks like. It looks like this, apparently. It looks like it's continuous, which means it actually could be defined everywhere. Notice the scale here, 0.49, 0.51 over here. It looks like it's very close to half, actually. Takes the value exactly half at only 2 points, 1/4 and 3/4. This actually shows that this is actually a bunch of dots. This is 2 to the 12, 4,096 dots. That's all this is. I didn't join them by line. And from what you've all mentioned earlier, in fact, we essentially do know that the 0, 1, 1, 0 portion is less than a half and outside bigger than a half. But we don't actually know that G is defined so well. But suppose that is true, then what does that mean? If we think of G as determining the harmonic measure, but you multiply G over and over again, right? And shift each time, you're going to be multiplying by some number bigger than half or less than half, depending on whether you're in this interval, 1/4 to 3/4, that's outside the middle, where it's larger, 0, 0, 1, 1, for most K, if this happens most of the time for most of the shifts. Or, in other words, so few changes in successive bits, right? A 0 followed by 0 or 1 followed by 1, that's most of the time. Whereas it's small when you're multiplying from the middle more often, which means changing bits. So if G really looks like that, that would explain the picture we saw where the more changes in bits you see, the smaller the harmonic measure. So is G continuous? I think it is. And I think it's doable, but I haven't really tried real hard. However, it's not such a nice function, apparently. So does it have a derivative? I think it has a derivative, but the derivative is a measure, singular measure. So the G is a function of bounded variation. Why do I think that? Well, here's a discrete derivative with step 2 to the minus 12 on the left and 21 times 2 to the minus 12 on the right. Doesn't look so good, but doesn't look so bad. That, I think, is all I have to say. And I'm out of time. So thank you very much for your attention.
Thanks, Russ, for the great talk. Questions?
I just want to mention the similarity to the Minkowski question mark function, which is the distribution for when you do this walk on SL, on SL2Z, you do a natural random walk and you converge to a singular measure, which is essentially this Minkowski question mark function, which is well understood. So that, that tree embedded in hyperbolic spaces is a little different from Muir's, but some of the phenomena are similar.
Uh-huh.
I would just comment on the similarity between this whole approach to some stuff that relates back to Lewis's thesis quite a while back. That if you look at that diagram of basically the pentagons in the hyperbolic plane, which is what you have, then there's this old question of Brodsky that you put a dot in everything in every other row, and you ask, well, what's the density of the dots? And you can make a fundamental domain where you look at that row and its parent, in which case 2/3 of the pentagons have dots, or you can look at that row and its children, and then you say 1/3 have dots. And you had something very similar when you had your infinite tree, where you said, well, what fraction of the things are red or black? And the way out of the mess is to look, to get an unambiguous answer, is to look at some sort of invariant measure. Now, Lewis's thesis was different, was looking at SL2R invariant measures, and this particular graph wasn't seen by any invariant measure, but you're looking for some sort of invariant measure with appropriate notion of invariant, and that adjudicates between the different paradoxical interpretations of what's going on in this hyperbolic structure, which in turn is that not that far from the concepts involved in Sophic entropy. So it's this stuff that you're doing is tying into a whole lot of other interesting stuff.
Yeah, so I don't know if you were here, but before I started, I mentioned that I was thinking this morning of some other questions because of the title of your seminar. And in fact, I think there are some similarities with what you just mentioned. So remember this graph, this dyadic lattice graph, when you naturally put it in a hyperbolic disk or plane, has this distinguished boundary point. And that is not good if you want something to be invariant under a group of isometries of the hyperbolic plane. So,
right, and that's exactly the thing that makes it not seen by the various measures.
Yeah, that's right. Now, first of all, so this was an example of a graph that was stationary for random walk, but not unimodular, and did not have a stationary dual. Okay. Whereas all unimodular planar graphs do. Now, the question is whether this is a special example in some sense, or whether this is, in fact, what always happens. In other words, if we have a stationary random rooted graph whose dual does have a stationary measure, must it be unimodular? Okay. Now, what does that reduce to? I think it may reduce to something like the following. So to talk about what you were talking about, Lorenzo, is there a group, can we say that our unimodular random rooted graph that is naturally embedded in the hyperbolic disk is invariant? Does it have an embedding that's invariant under an isometry group? Well, no, because it's a root. There's a distinguished vertex as a root. Nevertheless, you could consider whether after you compactify or take a quotient appropriately, you have an invariant measure. It seems likely to me that the unimodular case is exactly when you do. And when you don't, if it's stationary, and when you don't, that could be possibly used to show that there's no stationary dual. I don't know about that. But anyway, it's another question of distinguishing between unimodularity and stationarity in this for the planar case. So we're looking for more group invariance. Any questions? Are you still recording?
Yes.
People may be shy if they know they're being
Yeah,
recorded.
I can stop recording now.